This came up yesterday. Mark had a question that is going to drive this next little portion here, related to making sure you understand how leads of an EKG look at the heart. Because we're going to move forward and deal with axis today, the first part of axis. Okay? So how leads look at the heart. Okay? So when we put leads on somebody, when we actually put the electrodes on their body, we have one on the right arm, one on the left arm, one on the right leg, and one on the left leg. Right? The right leg is always the ground, and the other three are live electrodes. Understand? We all agree? Okay. What I and Tobin discovered through studying Da Vinci and cadavers and everything else was that when you put 3 electrodes in those particular 3 places, based on the anatomy of the heart, it creates, electrically speaking, an equilateral triangle with the point straight down below. So the left leg, instead of being on the left, as it pertains to the heart, it's directly below the heart. Does that make sense? That's electrically these 3 spots being what the, adding into the anatomy of the heart and being able to be placed over the heart. That's the triangle that it created. Okay? It goes a step further though. When we're doing this, this triangle still kind of denotes where the electrodes are on the body, not where it's reading the heart from. So electrically speaking, and we have to spend like a week on this to understand the electrically what's going on. But electrically speaking, this triangle does not show you exactly what's happening on the heart, because if we superimpose everything over the heart, everything comes from the middle of the heart. So this line right up here is not above the heart, it goes directly through the heart. Electrically, that's what it looks at. Okay? So when we put the negative on the right arm and the positive on the left arm, and our camera, which we've already discussed, is always sitting on the positive and looking directly at the negative, right? We don't have a camera sitting above the heart looking over here on top of it. That camera is actually going directly through the heart. So this is the negative, this is the positive. That's my camera. Does that make sense? Electrically, that's what we see. This line moves over to the middle of the heart. Where the negative was up here on the left arm and the positive was on the left leg. So the negative is up here, the positive is down here. So this is my camera. Does that make sense? And of course, this one is moved over to the center as well. Where the positive is down here and the negative up here. So this is my camera. Does that make sense? Electrically speaking, when we put the electrodes in these spots, that's what we see. That's where the camera actually takes the picture. And you just have to get past the confusion of the fact that electrodes are on wrists or arms or ankles or hips or whatever the case is. You just have to get past that. Okay? Do we understand? Everybody good with that? Okay. The augmented leads, then, you recall how they work?
Will you
Yes?
put the 1, 2, 3 up there?
I'm sorry, yes, I can. So this is lead 1, this is lead 2, and this is lead 3. And leads 1, 2, and 3 were simply named based on Einthoven's, the first ones he did, right? The first directions he did, right? So here's lead 1, here's lead 2, and here's lead 3. Good with that? Okay. The augmented leads, we found because we have this universal ground, and we only use 2 actual wires at any, we use 3 wires all the time. We have to have a negative, we have to have a negative, we have to have a positive, and we have to have a ground. We have to have 3 wires. Anytime we look at the heart, we have to have 3 wires. We have to have a negative pole and a positive pole, because that lets us actually see what the electricity is doing, and we have to ground it. If we have 3 wires, then we can see electricity, right? We can see the waveforms of an electrical current. Okay, but we have 4 wires. We have 4 wires going on, which means when we look at lead 1, we have the negative here, we have the positive here, we have the negative here, we have the positive here, which lets us see through the heart, and we have my ground here. This wire is not being used. It's offline when we look at lead 1. We have the negative here, the positive here, and the ground here for lead 2. That wire is just not being used. So as soon as we moved to a universal ground, which made sense because it changed, anytime you mix wires, there's always some crossover and some inefficiency with it. So when we were able to pull a wire and let it be stationed as a ground, it let us change the material we were using for that wire, which is good, to make it a better ground, but it freed up a wire. It freed up a wire. So then we started thinking, well, what if we put that wire back into mix? Why don't we use that wire then? So we still have the ground in the same place. We keep the positives in the same place, because we have to have the camera coming from one location, but we can change what we're doing with those negatives, right? So if I keep the positive down here, if I keep my positive down here, and instead of only making the right arm negative or the left arm negative, I make them both negative, then my camera is equally attracted to both sides. If it's equally attracted to the left side as it is to the right side, then it centers it. Does that make sense? So I make this negative and this negative, which forces my camera to believe that this is the negative spot. And therefore, I have that line. So now I have a camera that looks right here. Now, I want to proportionally make sure that this camera proportionally sees the same things that these cameras see. So I can't just augment, I can't just make this the normal negative. I have to augment those negatives to make this negative be the same polarity value as what this negative would have been. So this camera is being pulled in the same, proportionally the same way. So I augment these 2 negatives, I augment them both, so that this one has the same value as what the negative would be if it was not, if it was just in one place.
Augment just means change.
Augment just means increase the voltage
Increase.
up, or increase the polarity up.
How does it do these things all at the same time? Like when you look at
Because
the,
each wire has multiple wires in it.
and the one wire doesn't get like distracted by the,
Well, they're all insulated, and we've got,
Okay.
that's why you pay the money.
alright.
You pay the money for the technology of making sure that you've got conductive material that can do this. And so we have an augmented
That's engineering,
voltage
not paramedics.
lead with the camera on the foot. this is my positive, and these two are my negative, then I get my big negative right here, right? So in this particular case, we're talking about that one. There's my positive, my negative. Here's my camera. Oops. There's my camera. I have a lead that has augmented voltage with the camera on the left. Good. And if I make this one positive, and make these two negatives, so my negative is right there, then I have that line. Here's my positive, my negative. And there's my camera.
But really, they stop halfway through the heart, though, right?
No,
Here.
they do not.
Those are your V's.
They go all the way through.
Oh, that's right.
The negative is, because the negative is coming from these two, so it goes all the way through.
Must be thinking of
Does
something.
this make sense so far? Okay, because I'm using the same 3 wires to make these changes, the location of the wires doesn't change. The physical location of the wires on the person's body doesn't change. Which means every time I click it to a different view, every view is equidistant from the previous view because I haven't changed the wire locations. Which means every single one of the angles between any 2 views of it all have the same angle. Does that make sense? Y'all understand what I just said?
Can you
Restate it again.
I can, because the location of those 3 wires has not changed, and they are an equilateral triangle around my body, around that heart, then anytime I just change where I'm looking at it from, it's always equidistant from a previous one. So if I have my camera right here, it is equidistant from this camera and this camera, right? 3 different leads, all equidistant from each other. And when I split those in half with the augmented leads, then that means every single one of them is equidistant from each other all the way around. I have taken a pie and I have cut it 6 times into 12 slices. I have 12 equal slices of pie. And my 12 equal slices of pie, every single angle is the same. How many times does 12 go into 360? 30. So therefore, every single one of my cameras is 30 degrees away from another camera angle. Does that make sense? Right? You have 90 right here. Right? Those are my 90s. And they're split twice. So I have 30 degrees, 30 degrees, 30 degrees to make 90.
Flush,
And 30 times 12, 60.
flush.
Make sense? Okay, before I put numbers on here, is anyone confused? Everybody solid?
They might be.
What?
I was saying that they might be equidistant apart, but the cameras are still not equal. There's not 12 cameras. There are 6 cameras. So.
There are 6 cameras and 6 anti-cameras. Right?
Oh.
Because if I know what this looks like, what if I had a camera right here?
It
What
would
would
be
it
the
look like?
exact
Upside down.
opposite
It would
of,
be the exact opposite of
Yeah.
that. So I have 6 cameras and 6 anti-cameras,
Gotcha.
which means I know what each camera looks like, which means I know what the anti-camera should look like as well,
Yeah.
because it's the exact opposite.
Can you make an anti-camera via camera? Like, can a,
You only can in your head.
Wait,
Right?
some of us.
no,
can.
you can you do that with AVF or AVR when you put it on, make it AVL?
I'm not sure what you said.
Probably
And I
not.
understand the words you
Okay,
said.
so like, if you're looking at that picture, 3 AVF and 2 are all inferior pictures
Yes,
of your heart.
yes,
AVL and lead 1 are lateral leads.
Yes.
Okay, and then there's who the heck knows with AVR. So when the anti-camera of that be moving your AVR, oh no, I'm thinking of V4R and V.
Correct, we're
never
not
mind.
moving any of the leads.
Yikes. No, never mind.
Okay, we good so far?
I
So I need to apply some numbers
Why
now.
not?
I see where you're
This
going now.
picture, this is near, right?
Well, I see it.
This is what?
Near, like this would be a patient, so,
This is my person,
okay.
so this is their left, and
I
this
didn't
is
see
their
your
right.
person face.
We will always use our rights and lefts in relation to the patient.
Will you label
So
AVR?
this is augmented voltage on the right.
Okay.
Okay, so it's numbers time.
Yeah.
So when we look at a circle, our current measurement of a circle, for the most part, is done in degrees. And how many degrees are in a circle?
360.
We have arbitrarily chosen, through
360.
mathematics, 360 degrees as being a circle.
How do we arbitrarily choose through
Well, because
mathematics?
at some point in time, somebody in math labeled something as a degree
Okay.
instead of something else, and then said how much a degree is gonna be worth.
You could have done 100.
Okay, so we have 360 degrees in this circle. We are gonna put a label to that. We are going to say that this spot right here is going to be our starting point. Lead one, the lead one location is our starting point. So we're gonna say that that is 0. Sound good? Because we know the anatomy of the heart, and the electrical system, the SA nodes starting up here, ultimately the signal is traveling in this general direction. So we know that most electrical activity is traveling and happening down here in some fashion. So we are going to choose to start numbering our circle in degrees this direction. So we are going to label it this direction, where down here it's 90 degrees, and up here is 180. Right? So this would be
30.
30, this would be 60, this is
120.
120, this is
150.
150. Now,
Okay.
instead of labeling 360 degrees, we're, to show some relationship issues, we decided to not label it in 360 degree increments. We decided to label it in 180 degree increments only. And because we want to see some relationships and how the different leads are related to each other, instead of labeling all the way around back to 0 or to 360, we decided to come back to 0 and start again and label up this time in 180 degree increments again. And so instead of going from 0 to 180, we're going to choose negative numbers. So here is going to be negative 90, back down to, I should label it as 179 and negative 179. And we choose 180.
But there's no negative 180.
There's no negative one.
Okay.
We would just say 100. Okay? So therefore, AVL is at
Negative 30.
130.
negative 30,
Negative 60.
negative 60,
Negative
120.
negative
120.
120, and
Negative
Negative
150.
150.
negative 150. Okay? And now we've just gotten into what we call the axis. The axis of the heart. The axis is the overall average electrical activity, the direction that the electrical activity is traveling in a given part of the heart. Good? We okay with that?
Can you just say that one more time?
I can. The axis of the heart, the axis of a part of the heart, is the overall average electrical activity, the direction that electrical activity is traveling. The overall direction the electrical activity is traveling in that heart.
So most of the time it's 60.
Okay, so What lead do we look at quite often?
2,
And why do we normally look at lead 2?
just
That's
the
the way
average direction.
Because everything's traveling from top right to bottom left typically. Does that make sense?
Yeah.
So because it's generally traveling in that direction, we look at that lead because it shows us a pretty good, yeah, it shows us a pretty good example of what it's going. So most of our electrical activity is traveling in this upper right to bottom left fashion, okay? Now I need to split this up a little bit because I'm not talking about the heart as a whole now. I'm talking about portions of the heart. So right now I'm talking about the ventricles. Okay? Because the atria will have its own axis and the ventricles will have its own axis. So I'm talking about the ventricles. But the electrical activity in the ventricles typically starts at the AV node, which is found at the bottom of the right atria, and it travels to the massive left ventricle down here at the apex. So it's still traveling in that general direction. Do we agree? Okay, so the axis, the ventricular axis of the heart is most commonly down here in this general area. Do we agree that that's most commonly the thing in most people,
Yes.
based on what you know so far of your anatomy?
Yes.
Yeah. Okay. So here's what we do with the heart. To help label the axis, we're going to do two different things. We're going to do an easy thing and a harder thing. The easy thing is we want to know what the general quadrant is that the electrical activity of this particular heart is traveling in. So if I take this circle and I break it into quadrants, how many will I have? Okay, good. So we know what quadrant means, right? And I'm using the same labeling here. I had 0, 90, 180, and negative 90. Okay? So now I can break it into quadrants. Now, which quadrant, you can use up and down and left and right, which quadrant do most people have their electrical activity found in?
Bottom
Lower right,
bottom left.
Or left.
because it's a
Of the
person,
patient.
it's a
It's a
patient,
person.
not me.
Do I have to draw that?
There you go.
Oh, no. Right? And for Mark, it's more like this.
You got the
But
bugs.
perfect.
Got the
Is that a
bugs.
mirror?
That's a roll in your eyes. Okay. So, most people on average, right, would have their axis found somewhere in this quadrant. Would we agree?
Yes.
Excellent. What do you think we should name that quadrant then?
Normal.
Lower left.
We could name it either of those. Or we could use a word. Right? We could use that too.
Main.
We could use a word that's similar to sinus rhythm.
No.
Yeah, we could use that. Because this is the quadrant that most people normally have as their quadrant. So let's go ahead and name this the normal
Kind of slow.
quadrant. Sound good?
But then that only leaves us with abnormal.
It doesn't, because we can actually change that a little bit. So if their quadrant, if this is normal, but somebody's electrical activity is actually in this quadrant, where is this quadrant in relation to this quadrant?
To the right.
To the right. So we can call this the right quadrant. Well, that's pretty cool. Right not meaning correct, right meaning on the right.
To the right of normal.
And if this is our normal quadrant, but our electrical activity is here, where is it compared to normal?
Above.
Superior.
Well, if I am standing here, and that's to my right,
To normal.
what's this?
Left.
Left.
To my left.
Left.
So now I have my left quadrant. Does that make sense? Okay, so then we have this quadrant to deal with, right?
Left.
Abnormal.
Left quadrant.
So let's say that the electrical activity is coming up in this quadrant. for a moment.
Extreme right.
Yeah, so we.
Or is it extreme
so
left?
We have some, so that's, yeah, it's amazing. That's a question we'll have to ask. We're gonna call this one extreme right.
What?
And that's because anatomically, if you think about the heart for a moment, it's really difficult for the heart to do this in general. But electrically and anatomically, and I'll discuss how this is going to happen, it's easier for our heart to be shifted this way than it is for our heart to be shifted that way, anatomically speaking. It's hard for it to be shifted this way too, but we'll talk about that. So, we're going to call it the extreme right axis.
I don't think that's good.
Okay, so let's just, before we talk about how to figure it out, let's just think for a minute. This is my heart. If this is my heart and my electrical axis is here, because my electrical activity is traveling this direction, and I'm thinking anatomically right now, what anatomically might take my electrical axis and put it here? My electrical axis is here, and I'm asking anatomical, what anatomically might cause my axis to be there?
Tension.
How would a tension meter do
Shifting the part to the side of the thoracic cavity. Well, air pressure over
The
it?
right
What is
lung.
the air pressure of the lungs going to do to the heart?
there. Shove it
Shove it where?
that way.
Laterally.
Would Wolf
Towards-
Parkinson's white do it?
This way?
No, the whole thing.
This way?
Yeah.
Yeah.
How is that changing my axis?
It would look.
Would
So left
Wolf
hand.
Parkinson's white cause that?
Possibly, but Wolf
Swollen
Parkinson's
diaphragm.
white is not an anatomical change that I'm talking about. It's a physiologic change. I'm asking what anatomically would take my axis from here to here.
The heart's placement.
Yeah, the correlation between the SA and the AB. Shift it on.
You
What
shifting the leads?
anatomically can do it? What anatomical thing do approximately, I don't know, 100 million Americans have that might cause this to shift?
Obesity?
Yes, because what happens when they've got a lot of gut and that gut is pushing up on the heart? What's going to happen to the heart?
It tends
Yeah,
to
shit.
shift.
It's going to start moving.
That's not good.
What else anatomically could shift it that happens in half our population?
Pregnancy.
Yes, because that also does the same thing. Right?
Herniated diaphragm.
Possibly. What
That's why we put
could
that on.
anatomically, what kind of people might anatomically have a heart that shifts this direction? What kinds of people might have a heart anatomically that shifts like that?
Cirrhosis of the liver?
What's that?
Cirrhosis of the liver?
Cirrhosis of the liver being right here getting really, really hard.
Yeah, no.
Scoliosis.
I suppose their whole body would be. But that wouldn't shift the electrical activity because our electrodes are still proportionally
So nothing, not very many.
nothing.
Would it be the same people?
There's something,
like-
there has to
Same
be.
people.
The same population, if it's
Well,
moving
but
to the left,
Your heart,
it could push to the right.
your heart,
They'd have to have all their fat here somehow.
because your heart naturally shifts to the.
90s and market.
What would cause the heart to be able to do that? What would have to be in place in their gut to be able to allow that to occur? To their body, to their trunk.
It's the weird people that have all the organs flip flop.
Okay,
There's weird
I
people like
suppose,
that.
but that's a rare number of individuals, like 40,000 Americans total out of 350 million. But this is in, I don't know, a quarter of the population, a third of the population.
Pulmonary edema?
How would pulmonary edema shift the heart in one direction or the other?
Maybe equal on both sides, so.
Yeah.
And is that anatomical?
Yeah.
What would cause the heart to be able to do that?
Ligaments or things are holding it in place.
Pediatrics?
What about things that are holding it in place?
If,
I'm not thinking what you're thinking, but we're at least using the same terms.
dang it!
Surgery?
Okay, let's go back. What anatomically is shifting it this way?
Fashion or things in the
Sometimes
abdominal
physically-
cavity.
Okay, so what might shift it this
Absent
way?
of things, absent things?
Who might have an absence of things, and I'm not talking about actually removing anything. Because a third of our population hasn't had stuff removed.
Anorexic.
What's that?
Anorexic.
Yeah, what if they have less tissue down there? What if they just have less tissue down there? And we could use anorexia, although anorexia is not as common as this other condition that leads people really, really skinny.
Emphysema?
Yes, our emphysemic patients, they're skin and bones. They're very rarely have much meat on them. And their heart shifts to the right.
Third
Because
is
there's nothing
Americans
holding the
have
heart up.
emphysema?
So let's see if we use the fourth leading cause of death in the United States, so there's a lot of them. Does that make sense? Okay, so those are anatomical shifts. Anatomical shifts. Either something that's shoving the heart up and physically moving it, or something that's not allowing the heart to stay where it was originally designed and it's kind of shifting down. That might shift that. What are some things that might electrically shift the current? So I'm currently here, okay? And now my axis is over here. What electrically might cause that to occur?
A bundle
Ischemia?
branch block?
What bundle branch block?
Left bundle branch block?
So a left bundle branch block would cause my electrical activity to hang out on what side of the heart the most?
The right?
Right.
The left because
It would
it's
hang out on the
longer,
left
it's
side because it
sustained
takes longer.
The left because it's sustained longer. So what kind of bundle branch
A
block?
right bundle
Right.
A
branch.
right bundle branch block
Correct.
would shift my axis to the right. That's correct. Because the left will have done its job, and then I have nothing but right activity going on cell to cell. So it's hanging out over here more time. What else? What else would shift this direction?
Pacemaker?
Well, pacemaker should be set for right where I want it to be. So I suppose if I made it a right pacemaker. What else? Common.
Use your fingers to
Ischemia
show
on the
that
left
again.
side?
What's that?
Will you show with your fingers again?
Yep, I'm here,
Uh-huh.
and now I'm here.
Would hypertrophy do that? Because then there's more
Hypertrophy where?
right.
Right hypertrophy will shift it to the right, because I have more muscle mass over there. So therefore, I have more electrical activity happening over there. That's correct.
Oh, so if you have
Using
an
that same
emphysema.
concept, but not the same topic, what would shift it over there?
Ischemia?
respiratory disease,
So you just said hypertrophy, using that same general thought process.
Lack of-
Atrophy of the
Left ventricle.
left ventricle.
Absolutely. And what would cause atrophy or less muscle mass over there?
Ischemia.
Or go a step further, infarction. If our cells are dead, what are they doing electrically? So what are they adding to the average electrical activity?
Yes.
Nothing.
Nothing. So what's left?
The right.
What's over here? Does that make sense? So an MI, depending on where the MI is, will shift their axis one direction or the other, depending on where that MI happened. Bundle branch block shifted. MIs will shift it. Anatomical things will shift it, right?
You'll see more electricity in V3 than you will V2, potentially.
Quite possibly. Okay, so now let's talk about how to figure it out. The quadrants are easy. The quadrants are easy to figure out, for the most part, right? I don't care, one of you over there. You're positive, so you have what? Excellent, you're negative, and you could face her because that's how we would make it work. Okay. If this is my camera,
I can.
and I am the electrical activity, right? I'm the electrical activity, and I'm walking like this.
I see you.
What is my, you don't see me at all. She sees me.
Nice try, Mark.
How will I look in her camera on an EKG?
Possible.
Biphasic and,
Symmetrical.
yes, we'll just say biphasic is symmetrical unless otherwise said, but yes, symmetrical and biphasic, but also this.
Positive deflection?
Temporary, short.
Yes, small, as small as I can possibly be, because I'm in her camera angle for the smallest duration possible. Does that make sense?
Yes.
Because if her camera angle is this square, is the width of that square, right? If I move my body slightly this way or slightly this way, I'm in that square longer than if I'm going straight across it. I can't get across this square any faster than walking straight across it. Does that make sense? So therefore, I'm in her camera as small as possible and equally positive as it is negative. Does that make sense? So I am biphasic and small. Does that make sense? If I'm walking this direction, what am I?
Bigger, longer.
And
Positive.
positive. I'm as big as I can be and as positive as I can be. And if I'm in her camera angle walking this direction, I am
Negative as possible.
great. That's review. Do we all know that?
Yeah.
We're all good then. Okay, so now I'm here, right? Thank you. And I'm walking this way.
Not as big as you can be, but you're still positive.
Okay, I'm not as big as I can be, but I am still positive. Does that make sense? Okay, so I'm not as big, but I am more positive than any negativity that might be there. What if I'm here?
Not as big negative, but you're still more negative than positive.
Good. So I would be something like, I'm more negative than I am positive, right? But not as negative as I could be. Do we agree?
Why do you have
Would
a
you be
positive
negative first?
deflection if you're walking away from her or towards her? Why
This
are
is
you
just
not?
denoting which of the ventricles is firing first. That's it. I could have easily drawn it that way too,
Okay.
if I really wanted to, but I didn't want to. And I had to choose. So I'm back here again. I'm biphasic right now. Do we agree? Now,
Positive.
just barely. Do we agree? Just barely. So I'm like, something like that. I'm still small, but I am more positive than I am negative, right? And if I'm right here,
Small but more negative.
so this one might be something like that. Do we agree? Everybody understand all that? Good stuff. Okay, so when I label these in my head as I'm thinking of it, I would say positive, biphasic, negative, positive, negative, positive, negative. I'm labeling it as to which of them has which
Great.
amplitude is the greatest. Okay? We all get that? Okay, so if I have a camera, I have a line that goes across that camera. I can try to make that a better vertical line. What would we call that line, do you think?
Midline?
Biphasic line.
My biphasic line. It's not my midline because it's not the middle of the body, it's the middle of my electrical stuff. So I would call that my biphasic line for that camera. Do we understand that?
Mm-hmm.
Would that be your baseline? Would it be your biphasic line?
Don't confuse it with EKG.
Gotcha.
Don't confuse anything with EKG. I'm just doing it from camera angles right now. This is my biphasic line for this camera. That means if I had electrical activity that was on that biphasic line, right, then it would be biphasic. If anything travels on this side of the circle, anything. This, 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 this. Those would all be what?
More positive.
That means if I had an EKG that showed any of these places, it would be more positive than negative. Do we understand that?
Yeah.
Yes? And if it was anywhere over here, then it would be what?
More negative.
It would be more negative, slightly more negative than positive. So over here, it would be a negative EKG, and over here, it would be a positive EKG. Do we agree? Okay, so all I need to do is be able to find biphasic lines for my leads to know where they're gonna be positive or negative. So let's look at this for just a minute. It would be really cool if I could find leads that have these quadrant lines as biphasic lines. Wouldn't it be? Because then my quadrants are split up perfectly. Is there anything that has this line right here as its biphasic line?
Lead one.
One.
This is the biphasic line for lead one.
AVF.
Ah, yeah. AVF down here has this line right here as its biphasic line. Is there anything that has this as its biphasic line?
Lead one.
Oh, look at that, lead one. So what that means is that anything, I don't have enough colors. Maybe I do. I do.
There's green
I
over
do.
there.
He's got.
Anything that is traveling down here, any electrical activity traveling down here is going to make AVF what?
Positive.
Positive.
Positive. So AVF will be positive if anything is traveling on this spot, on this half of the circle. Does that make sense?
Yes.
And anything that is, this is a positive F. Right?
Positive F.
AVF.
F. Okay.
I'm just abbreviating. We good with that?
Yeah.
Okay.
That's a positive
And
AVF.
anything that has electroactivity traveling up there would make AVF what?
Negative.
Negative. I would have a negative F.
Negative AVF.
Yeah.
And I'm just gonna write
Thank you.
it. You bet. Is that better?
Yeah.
Okay. Do we agree?
Yep.
Okay. And anything that travels over here on this biphasic line, anything over here is gonna make lead one what? So I've got a positive lead one up here and a positive lead one down here. Does that make sense?
Yes.
And anything that's traveling over here is gonna cause lead one to be what?
Negative.
I will have a negative lead one here and a negative lead one there. Do we agree?
Yes.
And now I have a genetics quadrant. Did you ever play the game where your mom has blue eyes, your dad has brown eyes? What kind of eyes are the offspring gonna have?
Purple.
Fun to start.
Hey, Jenny.
Hey, so now you have it made, right? Because now I can look at a 12 lead, and I'm looking at two leads. I'm looking at lead one and AVF. If lead one and AVF are both positive, if their R wave is greater than any S or Q's that it has, if it's a positive lead, then my quadrant would be what?
It's normal.
Normal. If I had lead one as positive, but AVF was negative, then my quadrant would be
Left.
Left.
left. And if I had a positive AVF, but a negative lead one, my quadrant would be,
Right.
and if both of them were negative, my quadrant would be,
Extreme.
Left.
Right.
It's
I was trying to-
It should. It's a joke.
Way to
Does that make
confuse me.
sense? Do you understand? So, all I do is, initially, is just look at leads one and AVF. If lead one is even slightly more positive than it is negative, then I either have a normal or left axis. If AVF is even slightly more positive than it is negative, then I have a normal or right axis. And when I use both of them in combination, I can easily see which quadrant it actually is.
So So taking into account that this is a normal heart, if you have both positive, then you know that general electrical current is a normal current.
That's correct. If I have,
Without any sort of additional knowledge, and you could deduce that it's not ischemic, all things being normal.
Yep.
Okay.
and we call any shifting up here to the left, into the left axis, we call that a left axis deviation. Right axis deviation, meaning it's deviated from normal to the right, or deviated from normal to the left, or extreme right axis deviation, is the way that we just say that. So you'd say, I've got a patient with a right axis deviation.
Never mind.
You
Can
wouldn't just
you-
say they're
sorry.
rad?
What's that?
You wouldn't say they're rad?
No, what you could read it, right?
What is there, a lad?
A lad?
What would cause extreme right axis deviation?
So you might see a little bit of right axis deviation if you have a lot of right atrial hypertrophy.
But that wouldn't be extreme, would it?
Here's my,
Right atrial.
here's my AVR, right? I might see it if I have a lot of right axis deviation, a large MI across both parts of the heart,
Okay.
or a pretty serious trauma. Especially a trauma in someone that already has a right axis deviation.
Would you see extreme right if you are doing